Hello, my name is Pritesh Keshwara and welcome to my presentation on complex buildings and significant structures. Firstly, it is important to identify what defines a special structure or complex building. A complex building can be a project with high levels of uncertainty or ambiguity. It may have interacting parts, or there could be functional structures as well. Alternatively, there could be high levels of extreme sensitivity. Here is illustrated some examples of complex buildings. Going from left to right, there's the Shard situated in London, followed by the Burj Khalifa in Dubai, the Bank of America Tower in New York, and the Sydney Opera House. Each building is constructed in its own unique way and has its own special features, which makes it a complex building. Today we're going to look at the Petronas Towers. The Petronas Towers is situated in the city centre of Kuala Lumpur and it was officially opened in 1999. Here is some facts about the Petronas Towers. It began in operation in 1992 with the construction work and planning beginning then. Since it's opened, it's become 452 metres high, weighing at 300,000 tonnes with each tower. It must be mentioned that this was the tallest building when it was built. However, in 2004, it was surpassed by the Taipei 101 building to make it one of the largest buildings. However, it still remains the tallest twin towers. The project objective. The project objective of the Petronas Towers was to create an entertainment, commercial and business focal point to attract tourists at the heart of the city centre. In addition to this, it was identified that the project objective was to create a pair of gigantic skyscrapers. The project is identified as the home of Malaysia's national oil company owned by Petronas. The building is currently predominantly occupied by subsidiary and associates of the company. Architect. The architect of the Petronas building was a man called Cesar Pelli. He was an Argentinian architect who designed some of the world's tallest buildings and other major landmarks, such as the Pacific Design Center in Los Angeles and the Salesforce Towers in San Francisco. The project was initially estimated to complete in 8 years. However, Malaysia looked at ways to speed up the process and found a solution in which could see the building being built in 6 years. In order to meet the strict deadline, 2 different construction firms were hired and assigned to each tower. These 2 construction firms were Hazama Corporation, who was in charge of Tower 1, and Samsung Energy and Construction, who was in charge of Tower 2. Hazama Corporation were founded in 1873, and their headquarters is in Tokyo. They built the tower in a Japanese style, where Samsung Energy Construction was founded in 1970, and is headquarters in Korea using a Korean way of construction. As mentioned before, that both construction firms were under strict deadlines. To put into perspective the time frame, as the building of the Petronas building consists of 88 floors, it was expected that each floor was to be completed within a 4-day period. Here is identified the schedule of the Petronas Towers. Initially, the start of project planning began in 1992 in January. It took a year in March 1993 for the start of the foundation works to begin. This was followed by in April 1994 where the construction of the superstructure began. This was followed by 1996 the fitting of interior and complete with furniture. Shortly followed by the jacking of the spires of the towers 1 and 2. It was in 1997 where the moving in of the first batch of Petronas people began to move in. And finally, the towers officially became open when the Prime Minister of Malaysia opened in 1999. The initial proposal was for the Petronas Towers to be built on the former site of the Selangor Turf Club, which was one of the major horse racing courses in Malaysia. This was because the land was identified as flat and green, and therefore no previous construction had taken place. However, with the project taking up large surface area, a large soil investigation took place. This involved drilling over 400 boreholes into the earth. Evidence of the soil study showed that the original planning location was situated on the edge of a cliff known as Kenny Hill. The soil study showed that the bedrock sloped down as it began shallow at 15 meters and increased rapidly to over 180 meters. Typically, limestone can be identified to be strong as it provides good end bearings. However, in the case of the limestone, it was identified to have cavities in it and therefore causing soil problems. This was a major issue as over time, the limestone bedrock can cause unevenness and lead to large movement. As a solution, the construction firm decided to relocate the position of the building by moving 60 meters southeast of the initial proposal in order to obtain better support for the project, as illustrated in the diagram. Foundations can be used to support the structure of the load bearing to the layers of the soil or rock. In terms of foundation, the structure used a deep raft foundation. This is formed using long, slender columns made from reinforced steel and concrete. There is no surprise that pile raft foundations were selected as they are becoming increasingly popular when constructing high-rise buildings. The use of rectangular piles were chosen as opposed to circular piles. This was due to them having a larger diameter and therefore suggesting that fewer numbers of piles were needed. But having piles with a greater diameter meant that safety margins were increased, which ultimately reduced the probability of a problem occurring. The length of the pile raft foundations varied in size in order to ensure it stayed well above the unsettled limestone. In addition to being the world's tallest building at the time, the project also had the world's greatest foundation, with the largest steel piles being drilled 125 meters into the ground. This was almost 3 times deeper than the foundations used in the Sears Towers, which was the previous tallest building in the world. Piles were supported using a concrete mix. To fill the foundation, over 13,000 meters cubed of concrete was required. To put this in perspective, this is the equivalent to 5 Olympic swimming pools. As concrete is a material that is fast settling, the concrete was poured consistently for 54 hours non-stop to ensure that the foundation was strongly built and embedded. In terms of the floor design concept, the Petronas Towers are shaped based on distinctive Islamic art. In Islamic law, it is forbidden for pictures of people to be used. Instead, it used simple Islamic geometric forms such as shapes and designs. The Petronas Towers use 2 interlocking squares to create an 8-pointed star. This is called Rub al-Hizb. Originally, the floor plan design had a fundamental problem as its limiting squares limited the usable floor space in the building. Instead, each tower is supported by a ring of 16 cylinder columns which are of high-strength reinforced concrete. These cylinders are placed in the inner corner of the star-shaped plan as indicated in the diagram. The initial diameter of the column stands at 2.4 meters. However, the column gets reduced as they get higher up the building. In addition, the floor system consisted of a wide flange beams spanning from the core to the columns. A tube-in-tube system had been used for the lateral structure of the building. The system was introduced by Fazlur Rahman Khan. Tube-in-tube systems is used where to resist lateral loads such as wind. And the building is designed to act like a hollow cylinder. This is identified as extremely common in extremely tall buildings. A tube-in-tube system consists of a core tube inside the structural tube, which holds services such as utilities and lifts as well as usable tube systems on the exterior, which takes the majority of the gravity and lateral loads. The inner and outer tubes interact. This provides the advantage of increased lateral stiffness. The system is built using either steel, concrete, or a composition of both. In terms of external finishes, a total of 83,500 square meters of stainless steel extrusions and 55,000 amount of square metered of laminated glass were used to clad the walls. Designed as a curtain wall exterior, the cladding comprised of 33,000 laminated glass panels in all. Each panel is as high as one floor and spans from ledge to ledge. Stainless steel extrusions are used for these types of profiles due to the materials and wears and corrosion resistance. In addition to being essentially rust-proof, some grades of stainless steel are also immune to acid and other highly corrosive compounds, even in high concentrations. Laminated glass was preferred for its safety, sound insulation, durability, and solar energy control. Like the typical floor plan floors, cladding was constructed using the 4-day cycle system. All panels were interlocked and placed in a downward-upward position. Now we'll look at the special features. One of the key special features of the Petronas building was the Sky Bridge. The Sky Bridge connects the two buildings together on the 41st and 42nd floor. The tower hinge arch supporting the bridge has a rotational pin at the end of each leg and at the top of the crown of the arch bearings. The main bridge girds have a rotational pin directly over the arch crown to permit the crown to rise and fall as the tower moves closer and further apart from each other. Another special feature is the pinnacle. This is the crown glory of the Twin Towers with the pair of 73.5 metre steel columns that the pinnacles were, which propel the tower to the fame as the world's tallest building. Each pinnacle was comprised of a mast, a spiral ball, and a ring ball, all which were lifted piece by piece. It must be mentioned that the manufacturing for the pinnacles were made off-site and transported to the location. In terms of environmental features, the Petronas Towers uses highly strength fly ash concrete, which can reduce both the size and the weight of the building structural members. This can result in a saving of both material and the cost. Secondly, the Petronas Towers is made from a stainless steel structure that acts as both the internal and external structural framing. By using steel can mean that a large amount of savings in maintenance cost is saved. Constraints. In terms of constraints, engineers still face challenges in ensuring that the building remains straight when bundled up. The alignment of the building was checked every single day to ensure that there was no swaying. However, when the tower reached the 40th floor, one of the towers seemed to be swaying off tangent. This issue was resolved by overcorrecting the deficit in the opposite direction in order to cancel it out and lead to the corrective verticality. Another issue was when the engineers planned to lift the Sky Bridge into place during midair. The engineers decided to assemble the Sky Bridge during the time of torrential rain in Malaysia. It was decided the Sky Bridge should be assembled on the ground and lifted into place in one large piece. The technique used was to put the Sky Bridge into place using hydraulic jacks. The cranes were, unfortunately, due to the torrential rain, the cranes were struck by the weather, causing problems, which led to problems into the electrical systems. It was initially planned for the bridge to be lifted in 20 hours, but eventually took a staggering 36. In terms of material management, the skyscrapers are usually built with steel. However, steel is regarded as very expensive, and Malaysia had a shortage of it, as well as being very unfamiliar within the construction industry. Building a tower of such height with steel would have blown the proposed budget, and instead they opted to use a material which Malaysia had an abundance of, which was concrete. Concrete can be seen as one of the world's most common construction materials. A building made of concrete can resist strong winds and can absorb twice as much vibration than steel, and therefore suggesting it is much more stronger than steel. In terms of health and safety, by locating the bridge on the 41st and 32nd floor meant that in case of emergencies, individuals could relocate from one tower to the other. This ultimately halved the need for staircases. The design requirements stressed the importance of fire protection and life safety plan to seek compliance with the code. Minimum pathways of every floor identified that a minimum pathway of two pathways were required on every floor. In addition, although the Kuala Lumpur Fire Authority had has the responsibility to providing fire safety, it was recognised that the building must include integral building designs to ensure that risk of fire is reduced. This included a number of factors such as including sprinklers outside the building, smoke management systems, and various exit facilities. As Malaysia was a former British colony, they have been using the British standard as a code of practice within the construction industry. In conclusion, using a concrete floor along with a cylinder tube structure delivers to be a safe and effective method when constructing the world's tallest building. When considering all the constraints that occurred during the project, it was a remarkable achievement for the project to be completed on time. Thank you for watching my presentation.